Hello, I'm Maria Williams with the Collaborative on Health and the Environment. CHE enjoys bringing you the latest environmental health science through our partnership calls and webinars, science serves, publications, and social media. I would like to welcome everyone to today's CHE EDC Strategies Partnership Webinar, which is titled Emerging Chemicals in Food Packaging, Toxicological Profiling of Knowns and Unknowns. Our moderator today is Carol Kukowski, Executive Director of the Endocrine Disruption Exchange. We will leave time following the presentation for a brief question and answer session. You may type in questions through the Q&A feature available on the menu bar at the top of your window at any point during the presentation. After the presentation, our moderator will read out questions for our presenter to respond to. We will get to as many comments and questions as we can during the Q&A period. For those of you who called in on the phone, we have posted slides to accompany today's webinar on our website. You can download these by going to healthandenvironment.org. Please scroll to the bottom of the page and select today's webinar. On the webinar page is a link to the slides. Everyone on the webinar right now is muted with the exception of our moderator and our speaker. This webinar is scheduled to last for 30 minutes and is being recorded for our call and webinar archive. With that, I'll turn things over to you, Carol.
Thank you, Maria. I'm so pleased to be introducing Dr. Marie Vinggaard today. We have a very full call as many people are interested in this topic. Dr. Vinggaard is a professor at the National Food Institute, Technical University of Denmark, where she's an expert in molecular toxicology. She has over 20 years of experience within toxicology with a focus on endocrine activity of chemicals, cocktail effects of chemicals, and mechanisms of toxicant action. So welcome, Dr. Vinggaard. I'm going to turn the floor over to you so that you have plenty of time for your talk.
Thank you, and hello everyone. At the National Food Institute in Denmark, where I'm working, we have a great interest in food packaging materials, and we think it's a topic that deserves more attention. As we know, first of all, that food packaging materials can be a significant source of human exposure to chemicals. Just think of the endocrine disrupting chemicals, Bisphenol A, the phthalates, or the fluorinated chemicals that most, if not all, humans are exposed to nowadays. Many of those originate from food packaging materials. And secondly, there are large data gaps concerning the identity and safety of the majority of chemicals in food packaging materials. Previously, and still in some parts of the world, a one-week diet for a family can look like this, and most food is not wrapped in food packaging material. Today, a one-week diet for a family may look like this, where most of the food is packed in either paper or board or plastic or cans or glass. And despite this extensive use, there are currently large data gaps about the chemical composition of different food packaging materials and the human safety of the compounds in the materials. We know that chemicals can migrate to foods if they are in close contact with the foods, but they can also evaporate from food packaging and migrate into dry foods without any direct contact. For instance, can volatile compounds from a flour or sugar bag migrate to the dry foods? In the current EU regulation on food packaging materials, there's no specific regulation for paper and board food packaging. There is some specific regulation for plastic packaging, although the primary focus is on tests for mutagenicity and genotoxicity. So the present EU regulation is based on an approach that do not take into account endocrine disrupting effects or developmental toxicity, not to speak about cocktail effects of chemicals. So we have applied a bottom-up approach to evaluate compounds that we know are used in food packaging, but for which we don't know the exact toxicity. And we decided to focus on two chemical classes that we know are used extensively in food packaging and for which we are lacking knowledge. The one class is Bisphenol A analogues that are increasingly used for substituting bisphenol A, and also fluorinated chemicals that are used in paper and board food packaging. And then we applied a top-down approach to develop a new strategy for identification of problematic unknown chemicals in food packaging materials using effect-directed analysis combined with advanced analytical chemistry. The bisphenols, they are used for coating the inner side of cans and are present in cash receipts. And traditionally, bisphenol A has been used, but due to its toxicity, it's increasingly being replaced by other bisphenols that have a close structural similarity with bisphenol A. And we tested these structural analogues of bisphenol A, bisphenol B, E, F, S, and 4-cumylphenol. And they deviate by the structure of the bridge that connects the two phenyl rings. 4-cumylphenol is not a bisphenol as it lacks the one hydroxy group on one of the phenyl rings, but for simplicity, I call it a bisphenol. So human exposure have been shown for several of these compounds, and if you find a can stating that it's bisphenol A free, then there's a great chance that it contains one of the other bisphenols here. This is a simplified overview of the data where we have profiled the bisphenol analogues in a battery of cell assays. We applied reporterdine assays for the estrogen receptor, for the androgen receptor, the AH receptor, PPAR alpha, PPAR gamma, the reticnoic acid receptor, and an NIF2 assay for oxidative stress, a P53 assay to test for genotoxicity, and then we included an assay to test for effects on steroid hormone synthesis, and finally we tested the compounds for lipid accumulation in adipocyte. And the red color indicates an activation, whereas the green color indicates an inhibition or downregulation. And the gray color means no effect. So, and overall what we found was that all the bisphenol analogues, they were able to activate the estrogen receptor and to antagonize the androgen receptor. When it came to effects on steroidogenesis, we found that all the bisphenol analogues, they inhibited the synthesis of androgens, and they increased the level of estrogens except for bisphenol S, which had no activity on this endpoint. When it comes to effects on progesterone levels, we saw an increase for all of them except especially bisphenol S was very active on progesterone synthesis. When it came to effects on corticosteroid levels, we found a differential effect as most bisphenols, they inhibited corticosteroid levels, but bisphenol E and F, they actually activated the levels. And then finally, when we look at the effects on lipid accumulation in adipocytes, which is a kind of a screen for the compound's effects to induce obesity development, we found that all the bisphenols were able to increase lipid accumulation, and they had a potency close to that of bisphenol A. So our overall conclusion on these studies here is that the bisphenols, they have qualitatively similar endocrine activity with only a few exceptions. And therefore we think that substitution of bisphenol A with these analogues should be considered with caution based on these data here. The other chemical class that we have focused on is the fluorinated chemicals that constitutes a diverse group of 2,000 to 3,000 chemicals, some of which are shown here. The PAPs molecules, they are used in food packaging as in order to coat papers and board to give repellency properties to materials and thereby prevent soaking through by oils and water. So they are used a lot in fast food packaging for cakes, popcorn, etc. And these PAPS molecules, they are degraded by humans and also in the environment to fluortelomere alcohols that are shown here. And these are again degraded to the perfluorinated carboxylic acids that are shown here. And these perfluorinated carboxylic acids, they have really long half-lives, many of them in humans, which means that if we are exposed to these chemicals, then it takes typically many years before we get rid of these chemicals. And therefore we are concerned about this widespread use of PAPS molecules in food packaging materials because they give rise to these perfluorinated chemicals, carboxylic acids, which are very persistent. And toxicity are generally lacking for many of these fluorinated chemicals, and therefore we made a toxicological profiling of 4 PAPS molecules, 3 fluortelomere alcohols, and 9 perfluor carboxylic acids together with 3 technical mixtures. And we asked ourselves the question if these PFAS molecules had an endocrine mode of action. And here's an overview of our data. The molecules here are ranked according to their chain length. And if we look at the PAPS molecules and the fluortelomere alcohols here, we found that then they in general had an estrogenic mode of action. They were able to either induce synthesis of estradiol levels in our assay for steroidogenesis, or they were able to activate estrogen receptors in our ER reporterdine assay. They also, the PAPS molecules and the longer chain fluortelomere alcohol were also able to inhibit androgen synthesis and progesterone synthesis in the assay. Then when we look at all the perfluorinated carboxylic assays here ranked according to decreasing chain length, we saw in general they had a different profile. They all activated PPAR alpha and PPAR gamma in most cases, whereas they had no effect on the classical endocrine assays. And here's shown the results for the 3 technical mixtures. We had 1 technical mixture that was devoid of activity, and then we had the technical mixture 2 and 3 that showed a marked estrogenic activity, as they either induced synthesis of estradiol or activated the estrogen receptors. And this indicates that these 2 technical mixtures contain either the PAPS molecules and or the fluortelomere alcohols, which showed the same effect as these 2 technical mixtures here. So in conclusion, here we see that the subgroups of the subclasses of the fluorinated chemicals, they have different profiles, and that the PAPS molecules and the fluortelomere alcohols, they have mainly estrogenic properties, whereas the perfluorinated carboxylic acids that are the persistent compounds, they mainly activate the PPAR alpha and PPAR gamma. Yes. But then, what about all the unknowns in food packaging? How do we find them? And the aim of this study here was to develop a rationalized interdisciplinary strategy for the screening and identification of compounds with potential adverse health effects in paper and board food packaging. Before we did any experimental testing, we did a QSAR analysis, which is a computational modeling based on chemical structures. And it's like performing a weather forecast to see what the future brings. And we've performed this analysis on around 2,000 substances that we know are used in food packaging materials. And the outcome showed that around 20% of these substances, they had either genotoxic effects or mutagenic effects, or caused or were predicted to cause developmental toxicity, which indicated that there was a good reason to continue with our experimental studies. We selected the 20 food packaging materials made of paper and board, and we made a worst case extraction of these materials, and we tested these extracts in a panel of bioassays. And it was a panel of bioassays that is very similar to the panel of assays we used for the screening of bisphenols and fluorinated chemicals, many reported genes assays for endocrine activities, and an NIF2 screen for oxidative stress. And then we focused on genotoxicity, and where we used an assay for P53 activation, and we used an Ames test for mutagenic effects. And we tested these 20 food packaging materials in this panel of assays, and the overview of the results are shown here. We found a surprising range of activities. First of all, we found that all 20 materials were able to activate the AH receptor and the PPAR gamma receptor, indicating that either natural constituents of the paper are able to activate these receptors, or that all the papers are contaminated with, for instance, persistent organic pollutants that are able to activate these receptors. Then we found that 9 out of 20 materials were able to activate the estrogen receptor, and 6 out of 20 was able to antagonize the androgen receptor. 2 of the materials, the microwave pizza box and the popcorn bag, showed a positive Ames test, indicating that they contain mutagenic chemicals. And then we decided to focus on 2 of the materials for our further studies. We decided to focus on the pizza box made of recycled paper because it caused a marked estrogenic effect. And also we wanted to focus on the sandwich wrapper made of virgin paper, as it caused a marked anti-androgenic effect. So we, for these 2 materials, we fractionated the extract of the materials, which is step 3 in this overview here, and we tested the fractions in our bioassays. Then we made a tentative identification of compounds in the fractions, and by doing an expert evaluation of the compounds based on what we know of typical ligands for these receptors, and also based on the commercial availability of the chemicals, we again we tested the pure chemicals and quantified them in the extracts, and this enabled us to calculate the equivalence factors and for the food packaging material. And this is how a pizza box looks when it's fractionated. There are many colorful fractions of this material. So now we focus on the pizza box. that caused marked estrogenic activity. And here we found that fraction number 6 and 7 caused a marked estrogenic activity. And after having performed the whole procedure by tentative identification of compounds and verifying the presence of the compounds in the extracts and quantifying the compounds and calculating the equivalence factors, we found that 3 estrogenic compounds were present in the pizza box, and it was dibutyl phthalate, benzyl butyl phthalate, and bisphenol A. So these 3 compounds, they are estrogenic compounds, and they were found in the pizza box, and they could, when we did our calculations, they could, we found that they could, they were responsible for all the activity we saw, or at least we made it likely that these compounds were responsible for the full activity of the pizza box. And this may be because these compounds here, they are often present in recycled paper, and therefore they are present in this pizza box here. Then we focused on the sandwich wrapper, and we found a marked androgen receptor antagonistic activity in fraction 8 and 9 here. And after having done the thorough workflow here, we found that the 2 compounds, abietic acid and dihydroabietic acid, were present in the sandwich wrapper, and they had marked androgen receptor antagonistic activity. And by doing our calculations, we could show that they were probably responsible for the activity here in the sandwich wrapper. These 2 compounds, abietic acid and dihydroabietic acid, they are resin acids found in rosin that is present in pine wood. And rosin is present in some virgin papers like this sandwich wrapper, but is also added to paper, for instance, to be used for paper sizing. And paper sizing means a treatment that makes the paper resistant to moisture and makes it able to control penetration of printing inks. So it's added for almost the same purpose as the fluorinated chemicals is added to food packaging. And apart from being androgen receptor antagonists, abietic acid is also a 5-alpha reductase inhibitor, meaning that it has got dual anti-androgenic modes of action. And they have also been shown to affect spermatogenesis in fish. So we also did the migration studies of these compounds and could verify that they actually are able to migrate from the food packaging materials to the foods. So the take-home messages from this talk is that more focus on food packaging is needed, as it is a significant source of human exposure to endocrine disrupting chemicals, including persistent compounds. And a new paradigm is needed for hazard characterization of food packaging materials. And our approach is effect-based, covering endocrine disruption, cytotoxicity, and genotoxicity. It's quantitative and valuable for identification of emerging chemicals. And we identified abietic acid and dihydroabietic acid as androgen receptor antagonists in sandwich wrapper. And finally, alternative bisphenols have a similar toxicity profile as bisphenol A, and therefore substitution of bisphenol A with bisphenol analogues should be reconsidered. So thank you for your attention.
Thank you, Dr. Vinggaard. I really appreciate the pictures that you had and the simple explanation of what is a very complex paper. I'm going to ask a question to allow our listeners time to put their own questions in through the Q&A box, which is at the bottom of my screen, might be at the top of your screen, but you can just click on that and enter a question and I'll read it to our speaker. I wondered if you could comment a little bit on the fact that The bisphenols that you found in the pizza box, for example, you said that they were possibly or likely from the recycled paper, not necessarily from the manufacturing of the pizza box. And can you comment on that in terms of the bigger picture of what is coming up in recycled products in other types of papers that we interact with?
Yeah, as we know from previous studies that that bisphenol A is it's present in at least in many recycled papers, and I think it's more or less a general contaminant now, and therefore, like the salates, it's present in many recycled papers, and yeah. I think that'll be the case for many of these general contaminants that are around us.
Yeah. Okay. Thank you. So we do have a couple of questions coming in. One person writes, for all the chemicals investigated in your great studies, do we have any overview of safer alternatives?
Yeah. A good question. At least for the fluorinated chemicals that are used in food packaging, I know that there are more safe and just as good alternatives. We have a retailer here in Denmark who are trying to switch all the to get rid of all the fluorinated chemicals in their products, and they have succeeding in having the manufacturers of food packaging to produce packaging materials without fluorinated chemicals. So there are safer and non-persistent alternatives actually. For the bisphenols, I'm a little more. I'm not sure if we have alternative. I know that people are working on this issue at least.
Good, thank you. Another person asked, what are the practical and scientific challenges for making bioassays a tool for regulation of food contact materials?
What is the, can you repeat please?
The challenges, either practical challenges or scientific, for making these bioassays a tool for regulation?
Yeah, well, it needs to be accepted by the regulators to use these bioassays for screening of food packaging materials, and there's some conservatism in the system, so it takes it takes a while to convince authorities that it may be a good idea. I think there are a movement underway, so and I think they'll, at least within the EU, the European Food Safety Authority, they are now having more focus on food packaging materials. So I'm convinced in the future that the use of bioassays will be an important part of testing of the materials.
Okay, and have you come across any organophosphate plasticizers in your analysis of food packaging?
Organophosphate plasticizer, we haven't looked for that, so no, I cannot say that.
Okay. We have lots of questions. I'm trying to choose.
Yeah.
Do you know, can you talk about how much these compounds actually migrate to the food? How much do storage conditions influence the migration?
Yeah. How much the chemicals migrate is very dependent on the specific chemical we are talking about. I know for some of the fluorinated chemicals we have found that maybe around 10% of the chemical present in the packaging materials is able to migrate to the foods, but this number may be very different for other chemicals. The the extent of migration is very dependent, yes, on storage time, but also on the temperature and also the contact with the foods. For instance, if you have a packaging material that is intended to be used in a microwave oven, then there's a greater likelihood that the chemicals can migrate to the foods during the heating process. So I'm more, should say I'm more a toxicologist. I'm not a chemist, but I have colleagues that are more experienced in this part of it, actually.
Okay. Is silicon an option for substitution? What do you know about silicon? So many products are coming out now with food storage that are made out of silicone.
Maybe I'm not in a position to answer that question, actually. So, but it may
Okay,
be a
no
good idea.
problem. No problem. You aren't expected to know about everything out there.
No, but I can see there's a question on the green boxes and about the androgen activation going
Sure.
down.
You
I
can
just
answer
want
that one.
to comment that a green box does not necessarily mean a good effect. It actually indicates an androgen receptor antagonism, and this is considered as an adverse effect. So so it's still considered as a harmful effect, even if the color was green.
Thank you for clarifying that. And you're welcome to answer any question you see on here that you think is a particularly appropriate one for you to answer. I'm trying to pick through. We have 21 questions. We've never had so many before.
Okay.
And if you could stay on for a couple minutes, we don't want to take up too much of your time or other people's time, but we could ask a few more questions even though we're past the time of the call.
Yeah.
We do have a question about whether there's one. Go ahead. Go ahead.
Oh, there's one asking about the abiotic acid, and as it, you know, it arises from resins that arises from pine wood, and there's a question if we should be careful about using wood-based packaging, but I don't think we can say that. I think that with these levels we found in the packaging materials, they were relatively high. It's likely that this compound has been added to the paper for paper sizing, so it should be considered as an additive to the material, and maybe we should reconsider using these compounds as an additive to the paper.
Okay. Do you know if there are any efforts at the OECD level to validate the bioassays you've been using?
Some of the assays have been validated by OECD. For instance, the two assays we used for estrogen receptor activation and androgen receptor activation, they are validated by the OECD. Also, the assay on steroidogenesis, the H295R assay, it's also validated by the OECD, whereas the other assays are not. But yeah, I know there are several validations of in vitro assays underway at the OECD level, but it generally things goes very slowly, so it takes some years to validate these assays.
Okay, how about we ask one more, and then we can see, perhaps you could respond via, we might find some other way to respond to the people that had asked the other questions after the call. I thought I'd ask you if you know about downstream health effects associated with PPAR alpha and gamma activation.
Yes, that's a good question. That's a good question. We know the two fluorinated chemicals that we know most of, that is PFOA and PFOS, and they are potent activators of PPAR alpha. We are concerned about their human health effects. For instance, they are able to affect, they seem to be able to, PFOA at least seem to be able to affect the birth weights in newborn babies. It's known from human studies actually, and also there are indications that PFOA can affect cholesterol levels. PFOS is likely to affect thyroid hormone levels. It is likely that, or I should say, we don't know if these effects are mediated via PPAR alpha, but there's the possibility that that at least some of these effects are mediated via PPAR alpha. Otherwise, PPAR alpha activators, they are affecting lipid metabolism in the liver, and they can cause steatosis and stuff like that.
Wonderful. Okay, thank you so much for staying on a little longer, for the great presentation, for answering all these questions. Obviously, a lot of interest in this topic coming from a lot of different people doing work on these chemicals and curious about them. So I'm going to thank you once more and then hand the call over to Maria to close.
Great. Thank you so much, Carol. We are approaching the end of today's webinar. A video recording will be available on the CHE website soon, and tomorrow you will receive an email containing a link to the recording. CHE's next partnership webinar will take place next Wednesday, January 24th, and is titled At the Crossroads, Forging New Intersections Between Environmental and Reproductive Justice Through Research and Advocacy. This is the 5th webinar in our series, 20 Pioneers Under 40 in Environmental Public Health. You can RSVP through CHE's website, healthandenvironment.org. If you are new to CHE and would like to stay updated about upcoming events and more, please sign up to receive our newsletter by selecting the Join Us tab at the top of any page on our website. Additionally, if you appreciate these CHE partnership webinars, bringing you the latest environmental health research for free, we encourage you to support CHE's ongoing work by making a tax-deductible donation via our secure website. Again, our website is healthandenvironment.org. With that, I would like to thank our speaker, Marie Vinggaard, for taking the time to present today, and Carol for her excellent moderation. Thank you so much for joining us, and have a great day.